Hello, and welcome back to today's lecture. We finished the previous chapter, chapter 10, in the last video. I do have a few examples I would like to show you, but I would rather postpone that when we finish this chapter because there's no exercise or there's no homework directly from chapter 10. I will put maybe one or two questions together with chapter 11 on the next homework. So my plan is to go over a few examples from chapter 10 along with possibly a quick review of chapter 11 once we finish this new chapter. Okay, with that said, we're going to venture into a new chapter, chapter 11. The goal of this chapter is to study non-parametric distributions. So basically, how can we estimate the information we want from a given sample, and the technique we are going to apply is based on non-parametric methods, meaning we do not make any particular assumption on a parametric model. There are obviously advantages of doing non-parametric estimation, and there are also disadvantages. A huge advantage is that the non-parametric models are likely the most flexible ones, meaning they can be used to fit anything, right? Because it's not based on a particular assumption, right? So it has a huge flexibility. But on the other hand, just like anything in statistical learning, things with great flexibility tend to lose on interpretability, right? It's not exactly interpretable because there is no model, right? So we will see that obviously. The quick objectives of this chapter is listed down here. We will learn all of them, right? Let's start with the first one. So we begin with complete data because that is the easiest case for us to handle. There are a few standard like assumptions, or you can call it setups. We always have a sample of n observations from some random variable that is of great interest to us. It could be failure times, it could be claim data, could be claim losses. Anyway, we use small x to denote each observation since there are n observations, so it goes from x1 to xn. Just as what we already did in chapter 10, we would like to introduce the distinct values of all the n observations, and we use y. Since we may have observations with the same value, so the number of y's may be less than or equal to n. If m is equal to n, that means all the x's are distinctive. Right? But sometimes, some of them might coincide. So m can be strictly less than n. And we use wi as the count for yi. So w1 is the number of observations that have the same value as y1. Okay, so that being said, you should expect this summation result. Okay, and often it's very convenient to introduce the partial sum of the observations. So here is the partial sum. So it's actually cumulative, right? So by the definition, we know we're going to use GIs to express the CDF, right? So let's define empirical distribution. So those are the basic setup. Okay, you can call them assumptions, whatever you want to call them. And then we start to do the estimation. The empirical distribution of the given data is defined as the discrete So it's discrete distribution, which takes values y1 to yn with probabilities wi divided by n. So empirical distribution, basically you assume right? So that is the assumption, right? So you pretty much assume all the observations have the equal probability, and because we have n observations, each one must have probability of 1 over n, right? So here is just another way of rewriting it, because some of them may be the same. The values may be same, so you should collect those same values, and when you collect them, the probabilities will need to be times by the corresponding factor, right? How many do you have? So that makes perfect sense. With that in mind, that's what they mentioned, right? Essentially, what you assume is all the observations have the same probability. With that in mind, we can define denoting the empirical PDF, empirical probability function, and the empirical CDF. I always use CDF. Okay. The definitions are rather trivial, right, at this point of view. So it's simply counting, right? You count. So for instance, if you want to know the probability at yj, you count how many x's, right, have the same value as yj. So it would be the count divided by the total number, which is small n. Okay, and to define the empirical CDF, we do cumulative counting, right? So you count cumulatively. So that's why it's not just the z count, right? It will be all the counts that below whatever you want, right? So since this is a discrete, right? We already mentioned in the previous slide that this is a discrete distribution. So you expect this kind of shape, right? So this is y1. So anything below y1 would be 0, and then you jump. You stay at y1 until the next value, y2, you jump again, right? So it's this kind of shape until eventually you reach 1 and you will stop at 1. So this is the rough shape of your empirical CDF, right? Okay, once we define empirical probability function and the empirical CDF, by the way, the notation is you put hat. So here is hat, F hat, and capital F hat. So you put hat. Okay. Once we have that, we can easily define the expectation, right? So the mean of the empirical distribution is, well, it's just the sample mean, right? It's just the trivial. And we can also define the variance, okay? But variance is slightly different from the sample variance. That's because we divide by n. So for sample variance, you divide by n minus 1, because for sample variance, when we define it as 1 over n minus 1, we will get unbiased. So here, that's because we want to get an unbiased estimator. Right? That means 11.4 is a biased estimator, right? That is a biased because it divides by n. In order to make it unbiased, you need to divide by n minus 1. But the difference is probably negligible if n is big enough. So when n is large, right, the difference it's almost nothing. So 11.4 and the sample variance, they tend to be very, very close, right? Of course, you can tell by this. Right? Here, basically, what we do is first moment and second moment. Of course, here's second central moment. You can easily generalize, right? You can go to any moment that you want, right? So you can do third moment, you can do skewness, you can do cadusity, you can do anything you want, right? This is because you already know the probability, right? Once you know the probability, of course, you can define to any moment. In fact, we can also do censored, the censored moment if you want, right? So censored means you're going to cut on the right hand side. Beyond this point is simply U, right? So we just need to discuss where this U is located. So assume this U is between two observations. Then we know beyond yk, you simply make all the values to be equal to U, right? That's the limit. So that is the reason why you have this probability. So it's basically 1 minus the previous CDF, right? The previous CDF at this point, right? So that's the survival probability, right? So the survival probability times the limit. Okay, that's the censored part. Obviously, this area stays the same, right? Because for this part, x is actually smaller than the limit. So everything's straightforward at this moment, I believe. Once you define the empirical CDF, obviously you can define the empirical survival function, right? In the same way as we define survival function, right? Just the 1 minus the CDF, okay? One thing some people don't like about the empirical distribution is that easily illustrated by this graph is that this is discrete, right? It jumps. It goes from 0 to this line and then stays it for some time and then goes up again. Some people don't like it because they really dislike these continuous graphs. So one way to gain continuity is to do a simple linear interpolation. So we do linear interpolation, we will get y hat. So we already have two notations. Y tilde, excuse me. Originally we have y hat. Y hat is empirical. Okay, y tilde is what we call the smoothed. Although the name itself is a little confusing because it's not exactly smooth over the entire region, right? It is piecewise smooth. Okay, when we try to make it nicer, what we do is very simple, right? Let me go back to the graph. So instead of jump directly to the first point, we can do this, right? So basically what I do is to connect, right, from each point to the next jump point, right? I do not want it to stay flat, okay, which I don't like, right? So I want to make it smooth. So between y1 and y2, there are many ways to make it smooth, right? The easiest way is simply to connect them. A straight line is a smooth graph, right? Although, if you look at the entire positive line, it's possible the graph may not be exactly smooth. Maybe it looks like this, right? So it's not smooth, right? For the whole region. But if you look at it piece by piece, each piece is smooth. So that's why I mentioned the name may be a little confusing, but overall it's fine. So basically what we do for the linear interpolation is to use a linear line. Right? It's to use a straight line to connect all the jump points. Right? That's it. That's what we do. Right? So using that idea, we easily see why we have 11.6. Right? So at those points, yj's, f tilde coincides with f hat, right? But between any two y's, we use a straight line to connect them, okay, instead of leaving it flat. So that's what we do. The weight, obviously, for yj, it will be the distance from the next yj plus 1 minus y. Right? That's very easy, right? So as long as you draw the straight line, you will see this. Another important concept is quantiles. Right? Quantiles are the key to VA, value at risk, and TIVA. We can use interpolation as well. But before we do any interpolation, first of all, we need to know what would be the quantile exactly at the y's, right? So that's what we do. So we use yj as the estimate for this level of quantile. This may cause a little debate or a little confusion because we actually divide by n plus 1, right? So here, we divide by n plus 1, not n, okay? The reason is because, well, there are a few reasons. If you recall what we did in uniform, x2b, I believe. Okay, so let's say this is a uniform distribution from to theta, right? So we can take the maximum order statistics. So which means this is the max of x1, x2, all the way to xn, and each one is an ID from this, right? So we see that this does not give theta, right? It gives something less than theta. To be precise, is right. So it's not exactly theta. It's actually strictly less than theta. Right. That means for the observations, you are unlikely to actually reach the maximum point. That is why we divided by n plus 1 to make it slightly under the empirical distribution. Okay, because for empirical distribution we divide by n. Here we divided by n plus 1, so we kind of manually lower the level a little, right? So that the maximum observation, in our mind, we know that it's not exactly the maximum of the distribution. For instance, for this uniform distribution, we know the maximum value should be theta. But however, when you do the random sampling, it's very, very unlikely you get exactly the theta, right? It will always be smaller. Okay, so that's why in order to account for that information, we divide by n plus 1. Okay, if you can also simply treat it as a definition, right? So basically, what we do here is for this level. So basically, is let theta, let delta be this level, then the quantile, okay, that will be yj. So all our observations will correspond to a particular delta, right? There are n deltas, right, corresponding to g1, g2, all the way to gn. A natural question is, what if the delta is not equal to any one of those? Then we apply the same linear interpolation idea, right? So it will always be between something, right? Between the two values. Of course, if it's beyond, well, you set it to the max or set it to the mean, right? So assume your delta is somewhere in between two values. You do the same thing, linear interpolation, right? So obviously they times by n plus 1 on both end sides. So at the bottom, you don't need to deal with another fraction number, right? So otherwise it would be wj plus 1 divided by n plus 1. So you times by n plus 1 for both numerator and denominator, okay? So this is the smooth estimator. Let's see, so here the notation is still x hat, although it might be more convenient to use x tilde, right? Because we use y, we use f tilde for smooth CDF. So, just pay a little attention to the notation. In other words, we only have one notation for quantile, which is x hat. But for CDF, we have two, right? One is hat, the other one is tilde. Okay, the next point is trivial. if all the y's are, or if all the x's are different, right? Then you just 1 from n, right? So that's trivial. Let's use an example to better understand what we have learned so far. Here we have a sample of 10 observations. Obviously, this is just to demonstrate the definitions of those concepts, right? In reality, you don't do 10 sampling, right? You don't sample 10 observations to do anything, right? It's far less than enough. First, you plot the empirical distribution and the smooth distribution. I use this little area to do it. The first one is 2, the second one is 4, the next level is 5. I mean, it's not scaled, so you know it's. I'm not good at drawing, but you should do a little bit better, you know, to scale your axes, right? So here it's not scaled, but anyway, we know the meaning. So here it's empty, and then I will need to jump 10% or 0.1 because it has a single observation at 2. It will stay at 2 for some time until 4. And then at 4, it will jump again to 0.2. So here's 0.2. At 5, it will stay for some time. And then we go to 8. Okay. So for 5, it's still the same, 0.3. And then for 8, you go up to 0.5. Again, you know, it's not scaled. And then you will stay until 9. Well, you can continue, right? This is the empirical, what I just did. The smooth, well, let's use a different color. The smooth, I use dotted line. Right, so that's smooth. You connect all the solid points. That's what you do. What's next? And we also need to draw the smooth quantile function. Well, this is slightly difficult. That's because well, it's slightly, right? You just need to divide by n plus 1. So you divide by 11. So at 2, so what is 2? So at point 2 is not 10%, right? So it's 1 divided by 11. So it's, let me use a different color again. Let's try this, a little brown. So it will be a little below. So again, I'm not drawing to the scale, right? So it should be 1 over 11 for my first point. So for this point, it's actually 1 over 11. And then for 4, it would be 2 over 11, right? So it will be 2 over 11. So obviously, I need to connect, right? So it will always below, right? But of course, my drawing is terrible, so it looks like a straight line. But you know, it's a little zigzag, right? So you know, it will have some turning points, but you see that my main point is that it will be below for the quantile function because you divide by n plus 1. It will be below your empirical curve. In my case, it will always be below my my pink point, right, at each solid part. Determine the, let me go back to our color. Determine the estimate f tilde at 7.2. Okay, for that, I first need to know, well, it's between 5 and 8. At 5 is 0.3, at 8 is 0.5. So it's in between, right? By the way, this is what we know, right? So that is f hat, okay? F hat takes the flat part between 5 and 8, okay? Now we want to do the, I believe we have the result down here, right? So you take the linear interpolate, right? Between 5 and 8, the distance is 3, and for the point at 8, you apply the distance to 5. Okay, it's exactly the opposite. So be careful of that. Otherwise, it's relatively easy, right? The reason why you apply that is, well, say here 7.2. 7.2 is closer to 8. So you apply more weight to 8 or F at 8, right? Less weight to F at 5 because 7.2 is rather further away from 5, right? So that's why you apply 0.8 divided by 3. Here is 2.2 divided by 3. So you can see the weight on F8 is much bigger than the CDF at 5. Right. So that is easy. Next, we want to know the 75% quantile. So first of all, remember it's 11. So we need to figure out the position. So this is easy to do, right? Well, what you actually need to do is to use n plus 1 times whatever the level you want, delta. This is 8.25. So it's between 7 and 9. Well, you may wonder why it's not between 8 and 9. That's because in this particular sample, if you count 1, 2, 3, 5, 6, 7, 9, right? So there is no 8. That's why it's between 7 and 9 instead of 8 of 9. Okay. We know 7 corresponds to what value? 11, right? 9 corresponds to 12. So the value here is 11 and 12. Then what do you need to do? Linear interpolation, right? So it's easier, right? So the distance between 7 and 9 is 2, and then you use 11 times delta to figure out which one is closer, right? So it's closer to 9. So for this point, you actually have higher weight than the other side. So it's linear interpolation, so it's easy. What's the next question? Estimate the censored variance. So we want to know the variance. So we start with mean. Okay. Everything up to this point is simply using empirical probabilities, right? And then we have 3 points bigger than 11.5. So if you go back to data, we have 3 points, 12, 12, 16. For all 3 values, we are going to use 11.5 to replace, and we have 3. So it's going to be 3 over 10. So that's why the probability is 0.3, right? So you merge them together and use 11.5 to replace, because once you take minimum, 11.5 is the minimum of with respect to 12 and 16. Okay, since we want variance, from here you can directly do the variance if you want, but it's often easier to do the second law moment, because you need to square all the observations, right? If you want to calculate variance directly, it will be 0.1 times 2 minus your mean squared plus 0.14 minus your mean squared, goes on. But you actually need to do subtraction before you can square. So it's probably easier to calculate the second law moment first, and then use the second law moment minus the square of the first moment. Then you get the variance, right? So that's a complete example, right? So it's actually very easy, right? I don't see any difficulty. By the way, here's the graph. We have dashed line that is smooth empirical. So this is F hat. Oh no, not F hat. Excuse me. This is F tilde. Okay. Those solid line represent F hat. Okay. Those are the empirical distribution. Those dashed line represents smooth empirical distribution, because it is smooth for each piece, right? And this well, it's a rather awkward shape. It's the smooth quantile function. That's because we divide by n plus 1. So it's always lower, right? It's always lower than your smoother empirical distribution, as you can see, right? This graph is drawn to the scale, so you can easily see it's not a straight line, right? So each piece is a straight line, but the entire shape obviously is not one line, right? So it's zigzagged all the way up to 1. We actually have an important point down here, but somehow so let me use additional slide to explain 11.14. So let me add a page to discuss the meaning from there, what it means by that result. So first, let's start with something easy. Okay, this big Y is the number of observations less than or equal to small y. Okay, this is how we define empirical distribution, right? So again, here is a random variable. The reason is because we haven't do any simply yet. We set up a model, right? We haven't done the sampling yet, so that's why it's a big Y. Okay, the big Y is here is a random variable. Okay, now what would be the distribution? So the first question is, what is the distribution of Y? This random variable, right? So it counts the number of observations that are less than or equal to small y. Okay, we don't know the true distribution, but we know it exists. Right? This is a true CDF. Okay, given any random sample, there are only two possibilities, right? For any random sample or xi. So it's either less than or equal to y or greater than y, right? And what is the probability? This means with probability fy, right? Here is with probability 1 minus fy. That is very straightforward. That is exactly the definition of CDF. Right? What is the CDF? CDF is the probability for your random variable less than or equal to some real value. Right? So here xi are IID copies of x, right? So for each one, it's either yes or no, right? So if this is a yes, this contribute 1 to the counting, right? If it's less than, it will be added to the count, right? If it's greater than, then this is no. So now you see what is a big Y, right? Big Y is the counting. So this means indicator function, right? So each indicator function is Bernoulli. Let me write it here, right? So it's very obvious that each indicator function is Bernoulli, right? It's either 0 or 1. 0 when you have this probability. 1, you have this probability. So they are ID. So this will be a binomial distribution with first parameter n, second parameter fy, right? Because when we sum up n independent, identical Bernoulli distributions, we get a binomial, right? So, okay, from here, we have all the information we want. Now, let me separate. For this particular estimator, so I'm applying what we learned in the previous chapter. Right? The mean of binomial is n times the parameter. Right? This is good. This means it is an unbiased estimator for the CDF we are trying to estimate, right? Which is excellent. Okay. Next, we want to calculate the variance. Okay, the constant has to be squared. So for this, it would be n theta 1 minus theta. So obviously, as n goes to infinity, the variance goes to 0, right? So when n goes to infinity, this goes to 0. So it's excellent. It's actually a consistent estimator, right? So it's very nice. Okay. Based on that, we are able to construct confidence interval. Okay. Of course, we need to apply a little approximation because so far we only know the first moment and the second moment, right? We haven't really started. We know what kind of distribution it is, right? We know it's a binomial, but we always trying to use binomial, not binomial. We're trying to use normal distribution to help us construct the confidence interval. That's because in old times we only have the table from standard normal, right? So that's the reason why we want to convert everything to standard normal, even though it may not be standard normal, right? But the good thing with binomial is when n is big enough, it's rather close to a normal distribution. So it's not that wrong. So here we construct 100 times 1 minus alpha percent confidence interval. So CI. So obviously this is a point estimator, and we need to plus minus. This is Z1 minus alpha divided by 2. This is from the normal distribution, from the standard normal. This is the quantile times by, obviously, times by the standard deviation. Let's copy. This is the true variance, right? Because we don't know Fy, so we always use our estimator to replace the true Fy. Okay, so this is a very important result. That's what's reported in the next page. So it's what's reported down here. So basically, I just proved, not exactly proved, but gave you the idea why this is the case. By the way, this is because when we do CI, we want the middle part to be 1 minus alpha, right? Which means I have half alpha down here, half alpha down here, right? So this is the point I want. And they are symmetrical, right? So this is Z1 minus alpha divided by 2. So that's why those 2 points will give me 1 minus alpha for a standard normal. And then I do standardization, right? So what I actually did is minus mean divided by, well, this is approximate for the standard deviation, okay? So the result we have here is actually approximation for the CI. It's not exactly the CI because the distribution is not normal, it's actually binomial. Okay, let's finish here for this video. We will continue obviously later on for more complicated stuff.